Is a non-calculator position question. We're given the velocity function, and our job is to take the initial position of 2 and add our displacement for the first second. So we're going to integrate the velocity function from 0 to 1. That will give us a new position. I'm going to integrate this by hand. For the sake of the video, I may skip a few steps here, but if I integrate that, it would be t cubed plus 3t squared. I want to plug in 1 only because 0 is going to give me nothing. So this would be 4. But because my initial position was 2, I'm going to add that. And so my new position after a second is 6. Number 2 tells me I have an acceleration function that is constant and 3. It then gives me one data point for velocity. It tells me that my velocity is 10 at t equals 2. The purpose of them giving me that is so that I can get my c value for v of t. So if I integrate this backwards, this would be 3t, but remember that integration generically involves a c value. And if I go ahead and take that 10 and plug it in for v, and then likewise plug in the 2 seconds that it occurs at, you'll see that my initial velocity, my c value, is 4. So that I can go back to my velocity function and change this to 4. Now if I read the question, I can actually answer it. It wants to know how far, so it wants an actual total distance is what this is asking me for. So it wants a total distance or a how far when the velocity went from 4 to 10. So I'm going to need 2 times. If I'm going to do a total distance, I'm going to need 2 times. I know that 10 meters per second occurred at 2 seconds. And now I need to figure out when 4 meters per second occurs. So obviously, if I just take my velocity function that I just found and set that equal to 4, you're going to see that t is 0. Subtract 4, divide by 3, we get 0. So there are my upper and lower limits. If I just take my velocity function and absolute value it, I will get my answer. If I were to go ahead and sketch the graph of this velocity function, you would actually notice that all outputs are positive, and so there actually is no space underneath that's negative. So taking the integral of an absolute value is typically done with the Math 9 button, but in this circumstance, I can simply just integrate this as if the absolute value is not there. So we're going to go with 3/2 t squared plus 4t. And again, the only number that matters would be the 2, since 0 will cancel itself out. So 2 goes in. I end up with 3/2 times 4, which is 6, plus 8. That's 14. Number 3, it tells me I have a position function of negative 5t squared. It wants the average velocity from 0 to 3. Now what we used to do first try is we used to plug in 3 to the position function and then plug in 0 to the position function. And this would give us 2 outputs, 2 rises, 2 y values, and then I would take my x's. Old school slope. This is how we did it first try. But now that I'm in second trimester of calculus, I learned average value can also be done. So we do 1 over the spread of the interval, and I average the integral of the velocity function. So if position is negative 5t squared, velocity is negative 10t. Now coincidentally, this math ends up being pretty much the same math as over here. So you can see that over here I end up with negative 45 over 3. And if I went through the same process over here and integrated it, I'd end up in the same boat. I'd have negative 5t squared integrated. I'd plug in my 3, plug in my 0, and subtract, and then take 1/3 of it, which again mathematically is the same thing as the red stuff over here. Number 4 is asking me to determine from this table which one of these position functions are represented. So these are position functions, which means when I put on my glasses, these t's will be the x coordinates, and these velocities will actually be the slopes. So which function shows this velocity behavior based on the times? Well, right off the bat, you'll see that I have a negative velocity right out of the gate. This does not have a negative velocity. It has actually a positive velocity. This also has a positive velocity. C, we're still safe. D, we're positive, that's out. And E, we're still safe. You can see here that at t equals 1, we have a positive velocity here. But at t equals 1, we look like we're horizontal. So if I go up here at 1, it's a positive velocity, so that means that it has to be C. Number 5, we get a calculator. What we're going to do is analyze the acceleration of this velocity function at t equals 4. That's a Math 8 question, so I think when you hit Math 8, what comes up is d dx. And then I want to take that function and plug it in, so we're going to go 3 plus 4.1 cosine of 0.9x. I'll close that parentheses, and then x we want to be 4. So if I Math 8 that, plug that in, that ends up being 1.633. All right, switching gears to an FRQ. This FRQ is a particle motion FRQ. A calculator is allowed, and what's important to know is that we have 2 runners. Runner A, all the values and data is coming from the graph. Runner B, all of the data that's in the graph for A, for B comes from this function. So 2 different representations of what's going on from a velocity standpoint. Letter A wants us to find the velocity of runner A and the velocity of runner B right out of the way. So if I go and take a look first at A and try to determine the velocity at t equals 2, that's simply asking me for the output. So if I go to t equals 2, I just go right up here and put a dot on the line. It's kind of hard to tell where the output is. You might think it's 6.5, you might think it's 7 or 6. To be exact, I think we should use the slope. So if I just go ahead and look here, I'm going up 10 and over 3. So every dot on this line has a slope of 10/3. So I'm going to just go ahead and write down 10/3 as a note. 10/3 as a decimal is 3.3 repeating. And so what that means is I can use this slope of 3.3 repeating over 1 to determine where I'm at 2. So if I just go up 3.3 and over 1, up 3.3 and over 2, so there I am at 6.6 repeating. That is my velocity for runner A. Now that's going to be in meters per second. To determine the velocity at t equals 2 for runner B, I can just plug that into the function. So the numerator would be 48, and the denominator would be 7. I think that comes out to be approximately 6.879. Yep, 6.857. Again, that's in meters per second. Acceleration, that's going to require slope. And on this one, math 8. So for letter A, we already kind of figured that out. Letter A, the slope of the graph at 2, we already did that before, was 10/3. 10/3 is 3.3 repeating, and that is now in meters per second squared. Letter B, I'm gonna do math 8, so I'm gonna go ahead and math 8 this and plug in t equals 2. And I'm not going to show all the work for that. I could also use the quotient rule and just go low d high minus high d low over low squared, and then just evaluate at t equals 2. But the actual acceleration there is about 1.469. And again, that's in meters per second squared. Total distance from runner A and runner B from 0 to 10 is going to require some integration. So I'm just going to go ahead and just go 0 to 10 absolute value of the velocity of runner A. And how I'm going to figure that out is just go to the graph and find all this space underneath, right? So right away we got a right triangle here that's 3 by 10. 3 by 10 divided by 2 is 15. Then I have a rectangle that's 7 by 10, that's 70. So if I add these two numbers together, this total distance covered is 85, and that would be in meters. For runner B, I'm going to use the function, so we're going to go 0 to 10. And we want the absolute value of the function, 24t over 2t plus 3 dt. And if I math 8 that one, I think I end up with a number very, very close, and that ends up becoming about 83.336. Again, that's in meters. I'll go ahead and get this velocity graph all set up in our calculator. I have Desmos, which I'm going to use. So here it is. When I plug it in, it's going to be really messy. On your calculator, it's going to be even worse. So I'm going to go ahead and adjust this window. It's nice I can zoom in like this. I believe that if you go back to the question, the interval is everything after 0. But if you actually scan the question, it looks like t is staying left at 2. So I'm just going to go ahead and kind of put this picture right around here. As kind of my service. All right, so let's take a look. First question is asking which direction the particle is moving, and usually particles are right and left, but it could also go up and down. So if I go to my graph and go to 1.5, 1.5 would be right in here. You can see that that velocity is positive, and since v of 1.5 is greater than 0, we are definitely moving up or to the right or forward. The justification should be written in a sentence as the velocity is positive at that spot. Now I got to find acceleration. I can already tell from looking at the graph that the slope at 1.5 is negative, but let's actually be specific. So what I would end up doing here is I would end up math aiding this. So I would ddx, and I would go ahead and use the vars tool and select that y1 that I plugged in. I could also just freehand plug in the function, and then I'm going to x equals 1.5. If I go ahead and plug that into math 8, that ends up giving me about negative 2.049. So I've got a slope of negative 2.049. Now, if I look at my output or my velocity, I could actually go ahead and plug that in. But what I'm going to go ahead and do is just say that this is positive. So since my velocity is positive, and my acceleration is negative, this is slowing down. But what's kind of tricky about this question is it's asking for velocity increasing. When we're talking about speeding up and slowing down, the direction does matter. But when we're talking about velocity increasing, the only thing we care about is acceleration. That is not the first and last time you will hear anybody say that. But in this case, because acceleration is negative, this is no, we are decreasing. So again, I know that most of you are going to want to say that, well, the signs are opposite, so that's my justification. But that's when we're talking about the word speed increasing or decreasing. Speed is non-directional. So all we care about with velocity increasing is the acceleration. So my justification for this specific question would just be because acceleration is less than 0. Given that the position at the beginning is 3, it wants me to find a new position at 2. So I'm going to go ahead and use, I've already done this once today. Let's take that initial position and let's add the displacement from 0 seconds to 2. And again, I want to go ahead and just vars and steal that y1 function dx. So if I go ahead and plug that in to math 9, I'm going to end up with about 3.827. So since I was already at 3, this 0.827 is actually the displacement that was covered for the 2 seconds, right? So the answer is 3.827, but it is important to know that that decimal is how far from where you was after 2 seconds. And then letter D, I'm going to go ahead and pull out another absolute value integral from 0 to 2. It needs to be absolute value. I'm going to go ahead and vars the y1 and dx. And when I do that, I end up with a total distance of 1.173. This is a very typical rate in, rate out question. This function given is the rate in, people walking into a health club. This function is the rate out of the health club, and we're going to combine these two functions together to analyze the situation. Another key number is that we have 29 people to start, and these two functions are occurring over the same interval, which is going to make things a lot easier when we start combining them. It says, is the number of people in the facility increasing or decreasing at t equals 11? Now, this language is asking for derivative language. That's first derivative, first rate. These are already in first rate. So if I just go ahead and I find out what E11 is, and then I go ahead and separately find out what L11 is, that will tell me everything I need to know. Now I went ahead and graphed these two functions. You can see here that at 11, the entry function is above the leaving function. So that's a dead giveaway that since entry is greater, we are increasing. My justification would be that the rate of entry is higher than the rate of leaving. To the nearest whole number, how many people are in the club after 20 hours? That's a three-part integration expression. So we're going to take the original 29. We're going to go ahead and add the integral from 0 to 20 of e. And we're going to subtract L. Because these two functions are operating on the same interval, I can combine them both in the same integral function. So if I type all that into Math 9, it gives me a total of about 56. Then it wants me to analyze where we have an absolute max. That's going to occur in one of three spots. The first would be at the start, which I think was 29. The second would be at the end, which we just found to be 56. And the third would be at what we call in calculus critical values. Critical values are when the derivative of our function is 0. Now I want to remind you that this part of the table is coming from that 29 plus the integral 0 to t of e minus L. So we're going to be plugging in these numbers to this expression. That's why it's 29 and we already did the work for 56. But let's go and take a look at critical values from the graph. Now remember, the derivative of this function would just be 0 plus e minus L. So e minus L is literally the derivative function of the situation. If I set this equal to 0, I have critical values. It might be easier on the graph to just set these equal to each other. So if I go to the graph, I'm looking for an intersection. This one makes no sense. This is the one we want, 14.664. So if I go to 14.664, I take that 14.664 and I sub it in to this expression up here. I'm going to end up with about 67. And there's your winner. Lastly, it wants to know when the health club has less than 10 people. I don't need to solve this. I just need to set up an expression. So what I'm going to do is just go ahead and write down that 29 plus the integral of 0 to, it wants me to call this now h of e of t minus L of t dt. You just want to figure out when that is less than or equal to 10, or in this case, excuse me, strictly less than. There you go. Oh, it does say less than or equal to, my bad. All right, for this question, you can see that we're kind of almost the exact same situation as the previous problem. The only difference is in this rate out question, the actual out does not begin until an hour later. So keep in mind that when we set up our integral and subtract these, we're going to have to make sure that that second integral is separated. So I'll show you what I mean. How many cars enter the parking garage from 0 to 10? That would be the integration of the e function. So we're going to go from 0 to 10 of the e function. So I'm going to just go ahead and I can vars that. I had to graph it anyways, so I'm just going to go ahead and say E of t. But if I just math 9 that, I end up with a value of about 510 cars. Now it wants E prime of 5. E prime of 5 is going to be a math 8 situation. So I'm going to go ahead and math 8 E of t. And then I want that at x equals 5. Now that's going to spit out the rate of the already rated function. That ends up being about negative 1.627. The units for that would end up being cars per hour squared. So what does that mean? Well, this is already a rate, right? So this is already a rate that cars enter. This tells you that that rate is decreasing. So the rate at which cars enter the garage is decreasing 1.627 cars per hour squared. The number of cars in the garage at t equals 10 is going to be a 3-part setup. So we're going to go ahead and just take the 230 cars and we're going to add that to the number of cars that entered the garage for the first 10 hours. Now we already did this, but let's just go ahead and show our work. That's 510, and then we're going to subtract, here's where it's a little different than the last problem, 1 to 10 of L of t. Now if I go ahead and plug these all in, I've got my 230. I already found this to be 5 of 10, and the math 9 on this one ends up being about 75. So add, subtract, we're at a grand total of about 665 cars. Again, we're going to analyze where we have an absolute max, and it's where the maximum number of cars occur. So let's look at all of our locations. We want to start with our beginning interval and the end of our interval, and then again, all critical values. So if I derive 230, I get 0. If I derive that integral, I get e. If I derive the next integral, I get negative L. And critical values occur when this derivative is 0. Just like the last problem, let's just find where the two functions meet. Here we go. I graphed it. You can see here that it's quite a mess, so I'm going to zoom in and I'm going to clean this window up. Remember that it's 0 to 10, so if I just go to the chain here and I cut all this off to negative 1 or 2 and stretch this to 12, this is the only number I care about, 2.521. So I'm going to go ahead and go 2.521. Now, to answer this column, you need to take that 230. You need to go ahead and add in the integral from 0 to t of e, and then subtract the integral from 1 to t of L. Nice part is at 0 it was 230. We already did the work at 10. It was 665. If you go ahead and take this 2.521 and plug it in there, and then plug it in there, that changes the number of cars to about 264. So you can see that the answer to letter D here is definitely going to be at the end of the day, 665.